Oh my god, oh my god, oh my god, oh my god. What is it? What is it? What is it? It's a VAX! Sit back, relax, and grab a snack. It's time to unpack and hack the VAX. Well, the first order of business was getting this thing up on the bench, and it is not a light machine by any stretch. It's too much for me to lift, but it's manageable with two people. The problem is getting it up and not getting your fingers caught underneath it as you set it on the bench itself. 10 fingers, 10 toes, all is good, and there it is on the bench where it goes. I'm going to take you through the entire journey today, from unpacking it to restoring it, expanding it, installing Unix on it, running it, and finally putting it on eBay where you can grab it as your very own. A few months ago, I found a VAX 4000 on eBay, bought it, then spent many late nights getting it working, configured, booted, installed, and set up with an operating system, and finally on the web. And when I was done, I moved the machine into my deck project area next to the PDP-11 systems. I added some Whopper lights to the front of it, and it happily trucks along running its own web page and running some cool screensavers. Then I noticed later that the same seller had an almost identical second unit available, and I was tempted, but do I really need another VAX? And the truth is I don't. Even though VAXen are built to be clustered, I've only got so much space to display things. And yet, I'd invested all those weeks learning how to set up a VAX and Unix, and I even had a spare CPU and memory boards from that project left over. I could leverage all that hard-earned knowledge. So what if I bought it, restored it, set it all up, got it on the network, and added the spare memory, and then sold it on eBay? And so that's precisely what I'm doing. You can find a link to the auction in the video description. And if your wife says that you can't have a VAX, feel free to remind her that Dave's got 2 of them. Now, my first step was to pull the power supply, check the voltages, and look for ripple. It passed all of my bench tests, so it was time to clean 30 years of patina off the machine itself. The front of the VAX features 2 doors, the bottom one requiring a key that nobody has ever seen. Rumors hold that you can get them and you can lock the VAX and unlock it, but I just kind of have to pry it apart. But now it's time to clean the VAX. The plastic is in fairly good condition, except for a few scuffs along the bottom here on the kick plate, and the rest of it is just dirt and grime that scrubs off with some simple green and a rag. Hard part is getting into these little vents here and scrubbing those all out, so I stuff the rag into the vent and give it a scrub. On the front of the case are what appears to be aluminum, or perhaps it's solder splashes, but whatever it is, like a shiny metal, scrapes off, and then I can clean the residue off that is left behind with some simple green, and there's no trace of it, but it was weird and I wasn't sure how to get it off at all at first. This VAX has the door off a 705A, which is my other VAX, and I have to swap them yet. To get this sticker off, I'm using a mixture of WD-40 and a plastic razor blade. Once I get inside the machine, I'm going to switch to a slightly gentler cleaner, in this case Windex, because a lot of it is sort of aluminized plastic, and I'm not sure that simple green is necessarily going to be good for it. So Windex I know doesn't harm it, and so that's what I'll be using on the internals. All of these little plug connectors and so on are terminators and drive identifiers. I don't want to get them wrong or lose them or get them put back in the wrong place, so I am carefully removing them one at a time, cleaning them up, and then reinserting them back where they came one by one. That way I can't get them into the wrong place. And then finally I'll buff up the power supply and the power switch and get ready to plug it in and turn it on. I've checked the voltages on the power supply. Everything seems good in that regard, so I generally just give it a shot at this point if the power supply is working, which it seems to be. But first I'll spiff up these SCSI hard drives. They're like a SCSI drive, but it's not in any way compatible with SCSI. It's just very similar to SCSI. It does you no good because it isn't SCSI, but at least you have some knowledge going in. Now, before I dive into the guts of this thing and start yanking out CPU and memory boards, let me set the stage with a quick tour through the VAX family tree and how we ended up with the powerhouse on my bench. It all started with the VAX 11780 way back in 1977, which, if you've never stood next to one, is basically a refrigerator that spoke fluent 32-bit. For assembly language programmers, VAX is pretty much heaven. It's got a huge orthogonal instruction set and plenty of full 32-bit registers. There's an instruction for almost everything, including even copying entire strings with a single instruction. DEC defined the 11780 as 1 VUP, or VAX units of performance, so it became both the machine and the benchmark. You didn't just buy a computer, you bought into an entire culture. Unibus and SBI backplanes, RA series disks that you could use as end tables, and Dave Cutler's VMS, which treated clustering and version files like common sense while the rest of the industry was still figuring out directories. From there, the line bifurcated. On one fork were the cost-reduced boxes like the 11750 and 11730, which leaned harder on microcode and had slower clocks so that universities and labs could afford a ticket to the big VAX party. On the other fork were the big dogs, the 8600s and friends, with gate arrays, deeper pipelines, and fatter buses like BI and XMI to keep hungry CPUs fed. I/O evolved in lockstep, with the humbler systems moving to the regular old Q bus while the heavy iron kept its more exotic fabrics. Meanwhile, DEC quietly rewired our expectations with VAX Cluster. Distributed locks, shared file systems, rolling upgrades. A room full of machines suddenly behaved like one resilient organism, and suddenly uptime wasn't a wish, it was a policy. The real plot twist, the one that leads directly to my VAX 4000, was when DEC shrunk the Baroque VAX instruction decoder into silicon and started folding whole cabinets into just a few boards. MicroVAX made it plausible, CVAX made it tidy with CMOS with on-chip cache, and then Rigel and Maria, or Mariah, I'm not sure, cranked the pipeline and added some memory bandwidth. And then NVAX arrived, which is the beating heart of the 4500 on my bench. So how does this 4500 stack up against the original 780? Well, in terms of raw performance, think 24 780s in a single compact box. But the fun is in the latency profile. The 11780 lived on long, shared buses with shallow caches. Every cache miss was like a field trip on the slow bus. The 4500 tightens up that loop with on-chip decode, snappy level 1 cache, a memory controller that bursts like it means it, and a Q-bus backplane that doesn't get in the way. Storage that used to mean mass bus and cabling that required a chiropractor is now SCSI or DSSI with honest-to-goodness termination and half the drama. Ethernet is standard, not a small active face secured by a third-party NIC and a software driver written by somebody who distrusted interrupts. What I love is the integration arc that you can see with a screwdriver. The 11780 was a city of wire wrap. The 4500 is a neighborhood on a single CPU module with NVAX at the center, caches right where they belong, and DRAM close enough to keep the pipeline always fed. System calls snap back, contact switches don't feel like shifting your old 3 on the tree, and I/O completes before the coffee cup cools. It doesn't trip your breaker, it doesn't sag the bench, and yet it's still unmistakably a VAX. From racks to a chip, NMOS to tidy CMOS, narrow caches to fast on-chip ones, exotic weird buses to SCSI and Ethernet, and clustering that turned availability from an accessory into an architecture. By the time we pop the cover on this 4500, we're not just meeting a faster VAX, we're meeting the distilled essence of 15 years of elegant DEC engineering, shrunk to something that I can move about without the shop crane. Now let's pull out the CPU and see where the magic lives. The CPU is held inside of this cabinet here, which is accessible via 2 screws and a turnout door. And once we get inside the machine, we discover that it is very unclean. Unclean indeed. A horror movie level of unclean. And so to clean it properly, I'm going to remove the CPU and the memory. That's 3 boards, 1 CPU and 2 memory boards. Here's the first memory board. And here comes the second memory board. They have a little retention mechanism that seats them nicely and allows for easy ejection once you pull both handles back. The card then just slides out. And I always have to fight with this door to get it off. Its little hinges, I don't know why. And then the cable that snakes back in here to go to the CPU board is very easy to break if you're not careful, so be careful. But once you're done, the CPU should slide out fairly easily. It'll hang up here a bit, but there we go. Comes on out. And you can see it's got 2 large packages on it. Now I'm going to go and vacuum the inside of this machine as best I can, and then use a paintbrush to get some of the finer dust out, and then eventually I'll hit it with some compressed air. After cleaning up the door and the CPU card itself, I'll insert the CPU back into the machine, slide it in. It will register at the back on the bus, and then these clips will help retain it and align it at the same time. And with the CPU reinstalled properly, I can then reattach the door to the system, which will give me a chance to then reconnect the cable on the inside, which I will have to use a flashlight to see what the heck I'm doing, but there we go. It looks like it's aligned and properly clicked in. Then I'll slide home the 2 memory boards and I'll click them in as well. Now there's actually a total of 3 memory boards going into this machine, but for now I'm just going to run it with the 2 that it came with. And with all the electronics squared away again, I will close the CPU door and latch it with the 2 screws. Then I'll be able to come through, find a power cord, and we'll be able to power this thing up shortly. Now you'll notice it's got an extra notch on it here. That signifies it as a 15 or a 20 amp cord, and you can't get away with forcing one in there that isn't made for it, so don't try. Lastly, we have the serial cable goes in and it goes to a DB9. Now if you're a member of the DEC faithful, here's where I'm going to upset a few folks. Because while the machine will happily boot into an image of OpenVMS, and You can even join it to a SimH cluster running right on your desktop. I'm not going that way. I'm installing BSD Unix, specifically NetBSD 10. Why Unix on a VAX? Well, it's for consistency mostly. See, I have a range of DEC hardware spanning many decades, and at the level I'm working on these machines, like custom kernels and so on, I'd need to be an expert on RT11, RSX11M, VMS, all at once. And since I'm not, I decided to run Unix on everything here. So that means the PDP-1134 runs either version 6 or 29BSD, depending on how I boot it. And the PDP-1173 features a fully customized 211BSD system. So it only made sense that as I extend to the VAX lineup, that I also try to run a BSD variant. And for what it's worth, even my Mac can trace its roots back to BSD Unix. So I'm not saying I've made the right choice, but at least I'm consistent. To get the machine running the fastest way I know how, I'm going to image my other VAX, which is already up and running and configured. And while I've paid my dues plenty of times fighting with disk labels, this time I'm taking the easy way out. I'm booting the machine from a disk image stored on an SD card housed in a Zulu SCSI emulator. That emulator is in turn connected to a real SCSI controller, and the system will be configured to boot off SCSI Unit 0. And the rest should be automatic. But to get to that point, we need a SCSI controller. And so I called up Mitch Miller at Keyways and ordered another batch of Emulex UC07 SCSI cards, which I use in pretty much every DEC system that I build. So let's get the controller installed. Now to boot this machine off of an image that's on a SCSI disk, which is on a SCSI controller, which is emulated by a SCSI emulator, we need a real SCSI controller. And that starts with the Emulex UC07, which I need to plug into the bus. So I open up this tray slot and oops, there's a cable which is routed through there, so probably not one I want to mess with. Let's find a more open and blank area where I can just insert the controller into the bus and hopefully it will work from there. When it comes to Unibus and QBus, there is a lot of import placed on whether you have it in the right slot, in the right bus chain grant order, and so on. I'm not sure how important that is on the VAX, but we're about to find out. I'm going to put it in the last open slot, and so it should pass along DMA and other such requests to the next card in the stack, but there are none, so it should just work. I'll plug the SCSI controller itself into the SCSI adapter or emulator, and then a SD card containing the boot image will go into that. But sadly, when I turned it on, it did not see the controller, so I'm going to remove the cards that are up front, and if I need to, move the SCSI controller to be the first card in the stack, rather than the last card in the stack, and see if it gets along better that way. First, I'll try it here just alone in the bus and see if that works, but alas, it does not yet show up. And so I'll remove the card, I'll make room for it up at the very base of the bus, and we'll install it as the first card in the bus once I've made room for it. And to make that room, I'll remove the network controller that is the first thing in the QBus. Now, there's also a network controller built into the main system, and that's the one I'll actually be using. It has priority because it's actually got a direct line to the CPU, as I understand it. But let's see if my SCSI controller will now be recognized. And sure enough, it is. Now, out of curiosity, I'm going to just move it down to the final slot and try it again and see if it still works with nothing in between. There is a card in between, but I'll make sure it's not actually inserted into the bus. So it'll just be the SCSI controller, and we'll power it up, and we'll see if it works. Now, getting the controller installed is just the first step. We next need to configure it, and it's not like today where you just bop on into a standardized BIOS system and select your boot drive. There's firmware on the card that we need to run in order to complete the setup, but the way DEC I/O works, the card only has a couple of I/O registers visible on the bus. So it can't just map a ROM into the system memory, for example. What we've got to do then is to establish a secret handshake with the card via those I/O registers. And if we get it right, that will signal the card to use DMA to write its firmware into the system RAM, and then we'll execute it right from memory. That running code will then update the non-volatile memory on the card itself to reflect the drives that we've actually got connected. If that process sounds a bit weird and arcane, that's because it is. And imagine how intimidating it was the first time I was confronted with it with just a card in my hand and a VAX on the bench. But now you can get to the front of the line and just watch me plunk in the numbers. Now what we want to do is bank switch in and talk to the Emulex SCSI card by doing some memory mapped I/O and depositing values in registers that will cause it to copy its code for its firmware into memory. We can then execute that code and we'll get into the firmware of the controller. Now we want to do the card setup and set the non-volatile RAM, which is section 14. We'll tell it to do an automatic setup and it'll just simply scan the SCSI bus and see what it finds and what sizes those drives are. Now on the SD card, I've got 4 hard drive images and 1 CD-ROM image, which should show up as address 6, and it does. So from there, we'll just pick the defaults for the rest of these options. So 0, and do we want to configure another one? No, we do not. We don't want to change anything else. And yes, we do want to set the non-volatile RAM. And that should be it. From that point on, it will write those parameters to the card, and the card will know how to boot up and present its list of drives. Now that we've got a boot drive and an image to boot from, if all goes well, we'll simply be able to tell the system to boot from drive DUA0, which corresponds to the first volume of our newly configured SCSI controller. And that's the place where I've placed the file HD0, which is my image of NetBSD that I originally set up and configured in the SimH emulator and then copied to the SD card for my first VAX. I'll have to make some tweaks to the networking once it comes up to distinguish it from the other machine, but it should otherwise boot straight into NetBSD. Let's find out. Now I've told the controller to boot from drive DUA0, and we'll see the NetBSD splash banner come up and a countdown, which I will let elapse. And from there, we'll see it spin up and boot NetBSD. And as soon as it's loaded the kernel, it will begin to execute it. And we'll see the banners from all the components coming up. Total memory, 65,468, so 64 megabytes. We see our RA1, RA2, RA3, RA0, our main drives. It's going to do a file system check, and it is clean. Now, of course, I've sped this up. The boot process on a VAX is rather lengthy, so I have just gone through and shown you the output and not the long delays in between. Now, I don't have networking active yet because I have to change the IP address before I can put it on the network. So we'll see a number of errors for name resolution on things like the NTP time daemon. As it goes through, it updates the fonts, and it's going to start mounting drives pretty soon, and we'll see it also mounting NFS. And it's going to go through and set the dump device. There are no core dumps, so it'll proceed through there, checking the message of the day, starting the NTP time daemon. Now you'll see a number of messages about panels here, and this is for the virtual panel that I built for the VAX that runs in a web browser. Unfortunately, I haven't installed the custom kernel that requires it yet, so the code is not able to find the kernel support it needs, and so we'll see a number of warnings about the panel not being found. Now we'll see the system services like the iNet daemon spin up, and we should also probably get cron, there we go, and the Apache web server. The mail system is started, and with that we should get to a login prompt. There we go, I will enter my name and my password. And like a USB cable, I always get it wrong the first time and have to try a second time, so we'll try a second time, and there we go. And with that, it should drop me to a shell prompt. I believe I have bash as my shell. There we go. Now I can run NeoFetch, and we'll see what kind of hardware we have installed. NeoFetch takes a long time to run, and I've sped that up as well. But you can see we've got 64 megs of memory, we've got a VAX 4500A, and here we'll run HTOP. And you'll notice under HTOP that the system is actually fairly busy, and that's because it's doing make map, and it's doing manuals, and it's doing all kinds of first boot activity that it has to do to produce some of the files that you will need to run NetBSD in the background. Once that's all complete, it'll settle down to just a few percentage points of CPU. When I want a VAX to feel less like a museum piece and more like a sneaky little Unix box that just happens to be old enough to rent a car, I reach for NetBSD. The magic trick is that NetBSD treats the VAX still today as a first-class citizen in a modern cross-platform world. Same tree, same toolchain philosophy, same release engineering. That means I can pull security fixes like any other architecture, only my CPU happens to be speaking microcoded poetry from the late 1970s. What modernizes the experience is everything around the kernel. I get package source, which is the package manager masquerading as a time machine. Pointed at a mere bootstrap, and suddenly a shelf of contemporary userland shows up on a machine that once dined mostly on Fortran and Bliss. Not every package will build on a VAX. Some, like modern Python, are just too heavy or assume vector units that the machine doesn't have, but the breadth of selection is ridiculous, and the dependency resolver does the hard work while I make coffee. If you need OpenSSH, tmux, modern shells, lightweight web and mail tools, or a tidy build environment, they're just a make install away. Compilers are where NetBSD quietly shines. GCC may not sprint on a VAX, but it's correct and well integrated, so I can recompile a userland or build my own projects with the same headers and libraries instead of spelunking through abandonware. And cross-compiling from a faster host is a supported lifestyle choice there too, so I can turn my desktop into a build farm and let the VAX do the fun part, just run the results. Day to day, it feels pretty civilized. Proper TCP/IP stack, sensible init, modern file systems and tooling, and man pages that still assume I'm smart. NetBSD respects the hardware without fetishizing it. The drivers are steady, the userland is coherent, and the updates are boring in the best way possible. On a VAX, that's the difference between curating history and actually using it. If you've always wanted a piece of old iron but wanted it booting turnkey and ready to plug into the network, check out the link to the eBay auction in the video description. I saved all the packaging and it's ready to ship. Until next time, thanks for joining me.
Do it, Glenn! Do it! Do it!